Okay, so just a quick reminder, we were talking about, at the end of last lecture, we were talking about system. Right? So using system to create a process from within another process. Right? So you can write a little program, which when you run it, runs as a process in Linux. Right? That makes a call to the function system. System can in turn call another another program, right? And that program will run, launching another process. Right now, at the end of the lecture, I told you you're not supposed to use system when you're trying to deploy software, right? So if you're just fiddling around on your computer, it's fine. So today I want to tell you how you should go about doing it. Where is it? 20 and 30. Okay, so now just before I tell you what the quote-unquote correct way of doing it is, I want to explain how to get the ID of a process. So remember that every process receives an integer ID, right, when it's created. The ID is unique for the lifetime of the process, right? So if you look at the processes that are running on your computer at any one time, the IDs of all the processes are unique. However, when the process goes away, that ID can be recycled, right? So IDs are reused over time. So the IDs are not they're not unique forever, right? So they can be reused. So the type of the ID is stored. So it's a type def, right? So the type def appears in sys/types. So that's not a standard C library header. That's one of the system headers. Right? So it's one of the standard Unix headers. Right? So in that header file, there's a bunch of types related to system types. Right? They're just a bunch of type defs. Right? PID T is one of them. So that's the ID of a type. It turns out it's just an int on my computer. There's a function called getpid, which will return the ID of the current process, of the process that you call it, in the program of the. So when you call getpid from a program, it returns the process of the program. Right? And that's declared in Unistandard, the Unistandard header file, right? Which is the Unix standard functions header file. And now remember, this is kind of important in today's lecture. Every process has a parent process, right? And so if you want to, you can get the ID of the parent process using getppid, right? And that's also in Unistandard. Okay? So they just return, both those functions just return an integer value. So here's a little program. So this is go to sleep again, except I've changed it a little bit. So this one will go to sleep for a specified number of seconds now. Right? So you write go to sleep n, and then the number of seconds, right? And then down here, right, on that line there, the program goes to sleep for n seconds. Now, I think the actual version of this is slightly changed. Let me just pull up Visual Studio Code. Okay, so in code, so the one I have on my computer, it actually gets the ID of the process, right? And then it gets the parent ID of the process. And then it prints them out. Right? So it prints out the process ID with the parent ID going to sleep now, and then when it wakes up, it says the process ID with the parent ID awakes. Right? So when you run this, so I'm just going to go to sleep for 1 second. Right? So it prints out its process 13658. Its parent is 6272. Right? And then when it finishes, it says it prints out its process number and its parent number. Right? That's actually a pretty wide gap between those two, 6272 and 13658. Normally process numbers go up by 1 every time a new process is created. So you can tell that my bash shell has been open on my computer for quite a long time. Right? So, oh yeah, let's take a look at that. PS, okay. So when you type PS to list the processes that I'm currently running, right? You can see here that the ID of the bash shell is 6272. Right? So when I run the go to sleep n program from the shell, right? The shell becomes the parent of that process. All right, moving on. Okay, so instead of using system, you should use execv or one of its relatives. So it turns out there's a whole bunch of these functions. They all do the same thing, but they all have different inputs. So I'm just going to show you execv. If you do man execv, you'll find all of the other variants of this function. Right? Now execv does something different than system. Okay? So execv, so if you type man, what you get back is that execv executes a file as a process image, which doesn't really mean anything, I think, with the first time you see it. Right? So what it's going to do, it will run a program, right? That you can, it'll run a program that's saved as a file, right? And all your programs are files basically on your computer, right? Now when it runs the program, it does something weird, right? So you're going to run the program from within another program, right? So what it does is it takes the program that you want to run, right? And it takes the program that's currently running and replaces all of its contents with the program that you want to run. Right? So all of the memory and everything that's associated with the current running program all gets replaced. Right? So the man page says that it overlays a file as a process image. Right? So that's really weird. So it replaces the current program that you're running with the one that you want to run. Okay? Now, they normally never return a value. Right? It doesn't make sense to return a value because it's going to replace the entire contents of your current program with another program. So even if it returns a value, there's no way that the current program can make use of it, right? Because it's going to replace the contents of the current program. The only time it returns a value is when it fails for some reason, right? So for example, when you call the function, if you give it a program name, if you give it an incorrect program name, or if you give it a program name that can't be run for some reason because it's not readable or executable or something like that, it can fail. Things like running out of memory can also cause the function to fail. Right? So in those cases, the current program is not replaced, right? And -1 is returned back to the current program. Right? But normally, normally you don't check for the return value on this function. So that's how you use it. That's its declaration. Right? So it does return a value. Normally doesn't return a value. Right? So if it succeeds, it doesn't return a value. Right? You pass in the name of the program that you, the name of the file corresponding to the program that you want to run. Right? And then this thing here, argv, right? That's the same. Argv is the same as the command lines that you would normally expect for a C program in the main method. Okay, so I'll explain that in a second. Now the signature of argv is a little bit, we haven't really seen one that looks exactly like this yet. Right, so it's char star const argv square brackets, right? Which is intimidating to look at the first time, right? Or even the second time or the third time or the fourth time you look at it, right? C takes a little bit of getting used to read these declarations. Okay, so to decipher what argv is, to decipher what anything is in C, the first thing you can do is try to read it right to left. Right? So when I read this right to left, I have argv square brackets, right? So I know that it's an array. Right? So that's what argv square brackets mean. So it's an array of star const. So const applies to the thing on the left normally, right? So that means constant pointer, right? So star const means it's an array of const pointers to, and then the last thing is char. Right? So a pointer to char is a string. So a const pointer to char is a string that you can't reassign. Right? So that means argv is an array of strings, and the elements of argv cannot be reassigned. So that's what it means. Right? So if you try to do argv1 equals some new string, the compiler complains. Right? So that's how to read that declaration there. Now all argv is, it's just the strings that you would normally expect to see in a C program from the main method, right? So if you write a main method that takes in command line arguments, argv should be those command line arguments, right? So argv0 is the name of the program, right? argv1, that's the first command line argument to the program. argv2 is the second command line argument to the program, and so on and so on. Right? So this function is trying to call that program using these command line arguments, right? That's what it's trying to do. Oh yeah, right. There's something I have not. It's here. Okay, so there is something missing here. Let me put it in. That's good. That's a good point. The last element of argv must be null. Thank you for pointing that out, because otherwise that's how it knows. Right? So it just iterates over the elements of the array until it sees null. Boom. Here we go. All right, so if I want to call go to sleep n using execv, right, I have to set it up as follows. So I'm just going to print out the ID of the process, right? Okay, then I'm going to set up my array of arguments. Right, now it should look like that. Right, so I'm going to set up char star const args. Right, it's an array, so I can use array initialization, the array initialization syntax to set it up. Right, and it's just an array of strings. Right, the first string, that's the name of the program. Right, it's not the path to the program. Right, when you look at argv0 in a regular C program, it's just the name of the program. Right, so you want that to be go to sleep n in this case. Right, I want to sleep for 5 seconds, so that's going to be my second command line argument. And then you have to have null here so that the function knows when to stop looking at the array elements. Right, to call execv, you pass in. So here's where you pass in the full path to the program. Right, so I'm assuming that go to sleep n is in the same directory as this program. Right, so /, go to sleep n will try to run go to sleep n in this current directory. It'll pass in these arguments. Right, so if go to sleep n decides to print out its command line arguments, it'll print out that, and then it'll print out 5. Right. Now, remember what execv does. It takes the contents of go to sleep n and drops it into this program, and everything that this program's doing goes away. Right, so this program never prints out hello. Right, it's here. Right, the compiler will happily compile this program, but hello will never get printed out. Right, because as soon as go to sleep n starts to run, it runs in this process's space. Right, and the contents of go to sleep n replaces everything that's in this program. Right. So we can run that. So that's execv demo. Right. So that's the execv demo process. Right. Now notice what happens. Right. The process number never changes. So when go to sleep n starts to run, right, it's not a new process that starts. Right. Go to sleep n runs in the current process. Right. So it still has the same process number. Right. The process number never changes. Right. The parent doesn't change either. If I printed out the parent here, it would also be 6272 in this case. Right. The shell. Right, so the program that you run simply runs in the current process space. Right, so it has the same process number, it has the same parent number, et cetera, et cetera, et cetera. Right, so that's the correct way to do it. Now, if you just look at this program, it's very weird. You'd say, well, why on earth would I want to replace the contents of a program with another program? Right, and that's because you normally don't use it this way. So I'll show you how you normally use it. Right, okay. So execv is not normally used the way I just showed you how to use it, right? Because it replaces the current process with a new one, and that's kind of weird, right? Like, why would I want to write a program that just replaces itself, right? So what you normally do is you write a program that uses execv, right? But the program starts a new process in which to run execv in, right? So instead, your program starts a child process. Right? And then the child process is the one that runs execv. Right? So how do you create a child process in any Unix environment? You use the fork function. Right? So that is the standard way to create a new process in Unix. Right? So when you type in ps-e or something like that, all of those processes that are there, they were started with the fork function. Right. Okay, now before I tell you about fork, I have to warn you about this, right? So when you fork a process, it's very powerful, but it's very dangerous because there's a maximum number of processes that your operating system can manage. And often what happens when you show fork to somebody the first time and they start to play around with it, they put fork in a loop somewhere and they end up creating lots and lots and lots of processes, which eventually brings your system to a halt, right? Because if you create too many child processes, right, eventually you'll run out of, the operating system will run out of process handles. So it can't create a new process. Right? Now, if you can't create a new process, you're kind of stuck because that means you can't kill any of the current running processes using kill. Right? Because to run kill, you need to create a new process. So you have to be careful about this. You have to be really careful about this when you go to run it on someone else's server, for example, because then you can bring down their server and they will not be happy about it, right? On your own computers, it's probably not a problem because you can just turn your computer on and off, right? If you're in the Windows subsystem for Linux, it's even easier. You just close Ubuntu or whatever it is you're running, right? So normally if you have physical access to the computer, it's okay. You just reboot, right? But avoid running this on someone else's computer, right? So don't log into a server somewhere and run a program that uses fork unless you're sure that your program is correct. All right, there's actually an attack based on fork. I forgot to put it in the slides, but there's something called a fork bomb. There we go, that you can look at here. So just Google fork bomb and you'll find a famous system attack based on fork. Okay, so what does it do? So fork takes the current process and copies it. Right? So it copies all of its memory, all of its resources, most of its resources, right? So basically it clones the current process to make a child process, right? The current process becomes the parent of the newly created child. Right? So when you write fork, a second process appears that's identical to the first one. The second process that appears is the child of the current process. Right? Now both processes run in completely separate memory spaces, right? So they have independent copies of their own memory. Right? It just happens that when you fork the process at that moment, they're equal. The memory spaces are identical. Right? Now what happens is that after the fork call, the parent process continues running on the line after the fork statement, and then the child process also starts running on the line after the fork statement. Right? So both processes continue running from the point after the fork call. Right? So here's a little example. Right? So I've got x equals 1 and y equals 2, and then I call fork. Right? So when you call fork in this case, two processes will now run. Right? So the current process will print out x and y, and then the child process will also print out x and y, right? And then they'll both return, and away you go. And remember, when they're running in their own separate memory spaces, right? So if you run this one, you would expect, based on what I've said, to get the value of x and y printed twice, right? So you do, right? Now you don't know which order these were printed in. Right? So you don't know if the first one was printed by the parent process or if the first one was printed by the child process. Right? So what you have to remember is when fork creates the two processes, right, the two processes are running, but they're running at the whim of the scheduler. Right? So you don't know which program is currently running when it actually prints something out. Right? Yep?
Can you not figure that out by using like the getpid?
Yeah, you can print out the PID. Yeah, but when you run the program, it may not always appear in the same order, right? So when you run it once, it might be the parent that prints out first, and then you run it again, it might be the child. Yep. This one's fork 2. What's this one doing here? Fork. How long is this one? Oh, okay, this one's fairly long. Okay, so you're up here. I'm going to call fork, right? Now, when fork returns, fork is funny. It returns twice. Okay, so this is bizarre. Okay, so remember when you call fork, the parent process and the child process are both running right immediately after this line. So the question is who gets this return value? Well, they both get the return value. They get different return values, okay, which is weird, right? So the child process gets the value 0, right? So that's the value that fork returns to the child process. The parent process gets the ID of the child process. Right. Let me skip over this line. I'll come back to this one shortly. Right. Okay, so this program continues. Right. So if the ID is 0, right, that means that's going to run in the child process. Right. So remember, fork returns two different values. It returns 0 back to the child. Right. So when this line runs, right, that can only run in the child process because the parent process is going to get a different value for child ID. Right, so when this one runs, it's going to print out some stuff here, right? So good. right? We have x and y here. The child process is going to change x and y, right? It's going to print out some stuff, and then nothing happens, right? Now the parent process, right? So there's else if child is 0, right? Otherwise, child is something else, right? So this is the code that'll run in the parent process, right? So we're going to get the ID of the parent process. We're going to get the ID of its parent, right? Of the parent's parent. We're going to print out the value of x and y, right? Notice the parent doesn't change x and y, right? The child changes x and y, okay? And so here, because the parent is running in a different memory space than the child, we expect the original values of x and y. Here, we expect the changed values of x and y. Right? So let's run this, and then I'll go back to that first if statement. So this is fork 2. Right? OK, so the parent runs. So that's process 15191. So the parent is 6272. Right? So that's my bash shell. So I can tell that this is the parent process that's running. Right? Also, it prints out the child process. Right? So that's the child process that got forked. Right? You can see that the parent prints out x is 1 and y is 2. Right? So its value of x and y has not changed. Right? Down here, this is the child. Right? So process 15192. Right? Its parent is 15191. Right? So its parent is the fork x2 program. It's the first fork x2 program that I ran. Right? And it changes its value, its copy of x and y. Right? Okay, now what's this line up here doing? If child ID equals -1. So fork returns -1 on failure, which normally doesn't happen, but it can. Right? So if it does happen, the child does not start running. Right? So if that doesn't, if fork fails, the child does not. There is no child process. Right? So now in the parent process, or in the original process, this is the code that runs. All right? Now, there's this thing here called errno, or error number, right, that you include using the errno.h header file. So errno is one of the mechanisms that C uses for error reporting. Right? So C doesn't have any exceptions. Right? It doesn't have any real exceptions anyway. You can sort of fake them, but it doesn't have any real exceptions. So the only way that a C function can report back that there is an error is by returning a value, right? So that's one way to do it. You can return a value, right? But that doesn't always work, right? So if you have a function that returns an int, and the function can reasonably return back any int, what value do you use for the error value, right? It's like, right? If you to return 0 or something, or integer max value or something like that, right? But those values might actually be meaningful. Right? So you can't really use those as, you can't safely or reliably use those as error values. Right? So the other mechanism that C uses is that there is a variable somewhere. It's declared up here. It's actually not necessarily a variable. Right? But there's a value called errno that a function is allowed to set. Right? So a function can set the value of errno, and then the caller of the function can look at errno to try to figure out what has happened. So errno is a variable that is set by system calls and some library functions when an error occurs, right? Some library functions, not all library functions, some of them. Right? Now, it only makes sense to look at errno when the return value of the call, of the function call, indicates that there was an error of some kind. Right? And remember that the return value from a function, you can't always safely decipher it as it being an error. Right? So most system calls return -1 if there's an error. The library functions are not consistent at all, right? So the C standard library functions, you have to look at every function to see what it returns on error, right? Most of them return -1, some return 0, some return null, and some return other values, right? So there's not really any consistency in how this thing works, right? If you want to look for I don't know if this list is complete. Right? But if you want a list of functions from the standard library that actually touch errno, you can click on that page. Right? And that page, that link also advises you on how you should use or how you should check the errno value. Right? So that's what errno is. All right. So fork is weird, returns twice. right? It returns two different values on success, right? Child process always gets back 0 as the return value. Parent process gets back the ID of the child process, right? The different return values let you separate the processes to determine, to perform different tasks, right? So by writing this if statement up here, right? By writing that, you can get the child to do something here, and then you can get the parent to continue doing something here, right? Okay, now there are some consequences to the way that fork works, right? So fork works by copying, right? Cloning the memory spaces of the parent process. Right? Now that means that it also includes, right? So when you clone the entire memory space of the parent process, that means that any data that might be sitting in a buffer somewhere is also copied, right? Which leads to weird stuff like this. Oh, I think there's a, yeah, here it is. Okay, so here's a little program. It does nothing, right? It prints out hello world, right? Then it forks, so it creates a child process, and then it ends, right? So as soon as you fork, basically the program ends, right? So a child process gets created, the parent process runs, but then they both return 0, and then everything goes away, right? Now the weird thing is if you run this program on a Linux machine anyway, right? Hello world probably gets printed twice, right? And it does, right? So it prints out hello world, right? Now the question is why does it get printed twice, right? Because there's only one print statement here, and it happens before the fork, right? So that print statement is line buffered, right? So output to a terminal in Linux is line buffered, right? So in other words, no output will appear until a new line character is printed, right? Notice there's no /n here, right? So no output will appear until a new line character is printed or the buffer is full and gets flushed, right? That's not long enough to fill the buffer, so it won't get flushed automatically. Right? There's no new line, so the output just sits in memory for a little while, right? Until the program returns, right? Now, when I call fork, I copy the parent's memory space. So I also copy what's sitting in the output buffer, right? So when you return down here, both buffers get flushed. The parent buffer gets flushed, and then the child buffer gets flushed. So they both end up printing out hello world. Right? And so, so you have to be a little bit mindful of that. Right? Oh, okay. So the other thing about copying or cloning the memory space to create a child process is all the file descriptors that are open, the child also gets a copy of those. Right? So when you run a C program, standard in, standard out, and standard error, those 3 file descriptors, they're all open for you, right? They're automatically opened by the system. So when you call fork, the child process gets the same file descriptors for standard in, standard out, and standard error, which lets the child process write to the same terminal as the parent, right? Which is good because that's the way your shell works, right? So your shell, when you type in a command, it forks, right, and runs the command in a separate process, right? It would be bad if the child process could not write to the same standard output or standard error or read the same standard input as the parent process, right? So this turns out to be useful in this case. Okay. Now, I showed you how to use execv, right? But I ran it straight from the parent process, right? I didn't create a child process to run it in. That's not the way you normally use execv, right? So the way you normally use execv is you fork a child process and then run execv from the child process, right? So that causes the child process program to be replaced with a new program, which is probably what you wanted to do anyway, right? It doesn't really make sense to replace the parent with a new program. And that's exactly what your shell does whenever you run a command, right? So when I open up the shell, oops, sorry. When I open up the shell and I type, for example, ls, right? The shell is a program, right? So it's a process. The shell is a process O, which you can see, right? So you can see it's process 6272, right? So when I type in something into the shell and press enter, right, it forks a process to run ls in, right? ls runs, process finishes, and then we come back to the parent process, right? ls can print to the terminal because it has the same standard output as the terminal, right, as its parent. Right? If you have a pipeline, ls pipe to grep for star.c, right? Each command in the pipeline gets forked, right? So ls gets forked, right? Another fork happens to run grep, and so you end up with two separate processes running here. Why did I not get, sorry, grep c? There we go. Right? So you end up with two child processes running here, right? So that's how your shell works, right? So your shell, when you type something in and press enter, right, it tries to interpret that as a command. If it's a command that it can interpret, it calls fork and runs the command in the child process. What's this one doing? I just have to quickly see what this one's trying to do. This one. All right. Okay, so the beginning is the same, right? I'm going to call fork at the very beginning. In the child process, I'm going to call go to sleep, right? So I'm going to use execv down here to call go to sleep, and it's going to go to sleep for 5 seconds, right? It's going to, when it calls go to sleep, it's going to print out its, the child process will print out its ID and its parent ID. Go to sleep n will print out the ID of whatever process go to sleep n is running in, right? Now the parent is going to print out the process, its ID, its parent ID, and its child ID. Okay, so we have to pay a little bit of attention to the output in this case. You'll see that the child. Okay. So this one is 4. All right. So there we go. So process 1664 with parent 6272 and child 161565. So that's the parent process, right? So that's when I run fork x4, its process number is 16164. Right? Now, the parent process calls fork, and then it execs the program. Right? So the child process is 16165. Right? Process 16165 runs go to sleep now. Right? So when it runs go to sleep now runs in the child process. Right? It replaces the contents of the child process, so its ID does not change. Right? But its parent changed. Its parent changed, right? So the parent of go to sleep n is apparently 6271, right? But the 6271, right? Wait, is that right? 6271, process 6272, right? But hold on, I just got to make sure I get this straight. 6271. With parent 6272. 6272, good. Process 16164. Oh, here it is. Sorry, I'm sorry. Look, so the child process has a parent 16164, right? When it calls exec, right, and runs go to sleep n, right? It go to sleep n has process number 16165, which matches the child process here. That's good, right? But it thinks its parent is 6271, right? It thinks it's 6271. Whereas the child process originally had parent 16164, right? Because 16164, that's the process that originally ran fork x4, right? The parent's changed, right? And in fact, the parent has changed to something that I can't see, right? So I can't see it right now. I'll show it to you in a second, right? In fact, it should show up if I do this. So I'm looking for 6271, which is right there, right? So it's init, right? Init was the process that started the shell, right? So the bash, my shell right here, right, was started by the init process, right? So what's happened is that the parent of that child process has changed, right? So it went from 16164 to 6271, right? Which is a little bit odd. All right, so if you examine the output of the previous program, you'll see that the child process parents change. Right? Now, why did it change? It's because the parent process finishes before the child process finishes. Right? So the child process, right, calls exec to run a program. That program sits around for 5 seconds. Right? The parent process just prints out some stuff and then it returns. Right? So the parent process finishes, but the child process is still running. Right? So the parent process finishes before the child process. So what ends up happening is the child process becomes orphaned. Right? So that's the actual word that's used. Right? Becomes orphaned. Right? Now every process needs to have a parent, right? But the child process here, its parent went away. Right? It finished, it returned 0 and then it left, right? So that child is now parentless, which is why they say it's orphaned. Right? So the way this works in Linux is that orphaned process becomes adopted by some other process. Right? In this case, it got adopted by that init process right here. Right? Now, exactly how this works, right, is way beyond the scope of this course. It's beyond the scope of the next course, too. Right? It used to be the case that when you orphan a process, process 1 would end up adopting it. Right? That used to be the way Linux worked, but that's not the way it works anymore. But in Linux, every process needs a parent. Right? So when your parent process leaves or finishes before the child process finishes, some other process has to adopt that child. Right? Now, so that's what happens if the parent finishes before the child. Now the question is, what happens if the child finishes before the parent? Right? So what if the child process terminates before its parent's process finishes? Right? Which is the normal way that things should happen. Right? So when a process terminates, its parent is responsible for reading the exit code of the terminating process. Right? So remember, when you write a C program, the main method always returns an int value. Right? When you run a bash program, right, it always has an exit status. So the way this works in Linux is that when a process terminates, right, its parent process is supposed to read the exit code of the terminating process. Right? And in Linux, that process ID of the child is not released back to the operating system until the exit code has been read. Right? So in other words, the operating system is holding on to this ID of this child. Right? And it can't use it for anything else. Furthermore, the operating system only has a finite number of IDs that it can hold at any one time. Right? So if a parent process does not read the exit code, then the child process becomes what's called a zombie process. Right? Even when the child processes finish, right, so it releases all of its memory back to the system, that ID that it had, it's still not released back to the operating system. Right? And the reasoning being because someone might want to know what was the exit status of this process. Right? And in Linux, that responsibility falls on the parent. Right? So the parent has to read the exit status, otherwise the child becomes a zombie. Right? So how can I arrange for the child process to finish before the parent? So I'm going to use the same program, except in the parent, right, I'm going to sleep for 15 seconds. Right? So that the child becomes a zombie. Right? So the child up here finishes in about 5 seconds. Right? Prints out some stuff, calls exec to go to sleep for 5 seconds. Right? Which means it's going to finish before the parent process finishes. Right? So if I use PS, we can see that child process, right, that's running go to sleep n, the operating system really does think that it's a zombie. Right? So let's try this out. So I have to get the timing down and I have to type in the right commands and everything. So let's see what happens. So this is 5. Right? Okay, so there it goes. So there's the child process. It's done. Oh, wait, I did this wrong. I already screwed that up. Okay, I have to run it in the background so I can use PS. Right, so here we go. Right, so it prints out some stuff. The child is done. Oh, what's going on? PSAUX. Oh, I got it. There it is. It's Z. Right, you can see it right there. Go to sleep N. Oh, that didn't help. Sorry. Go to sleep N right here. Its status is Z. So as far as the operating system is concerned, this is a zombie process. Right? It's a process whose exit doesn't help. I'm trying to get that to show up. Okay, you can't get it to show up. over here, oh, it doesn't say it. Beside that thing there, it should say defunct or something like that. But anyway, its status is Z. So as far as the operating system is concerned, it's a zombie process. Now, it stays a zombie until the parent finishes. Right? So the parent's now done, so that zombie process now disappears. Right? Oh, sorry. Okay, so the parent back here, right, has to read the exit status of all its children. Right? If it doesn't read the exit status of its children, those IDs are not released back to the operating system. That's a problem when you have a very long-running parent, right, that forgets to look at the exit status of all of its children. Right? So very long-running process would be something like a web server. Right? So if Amazon's web server, probably running Apache or something like that, those servers almost never go down. Right? If the code that's in there is written in such a way that it never reads the exit status of all of its children, eventually that server is going to stop being responsive because it won't be able to create any more children. Right? So exactly how you do read the exit status is the topic of the next lecture. Right? And we're also going to talk about how processes can talk to one another. But that's all that I have for today. Any questions? All right.